Hi, my name is Dr. Ahmath. In this video lecture, we are going to discuss about the applications of derivatives. In particular, we're going to talk about the linear approximation of functions using the polynomials. So we are given some function y is equal to the f of x, and we can evaluate this at some point x0. And what we want is we would like to approximate this function at some point near this point x0. So it is very difficult to evaluate this at the point x plus h, let's say. So I would like to give you a small example. So let's say you're given this function square root of x plus 1. And if I would ask you, could you please tell me what is the value of this function when x is equal to 0? You would just tell me it's easy, because if I substitute f of x to the f of x0, it is going to be square root of x0 plus 1, which is going to be square root of 1, which is 1 simply, right? So very much easy. But if I say what is going to be the value of this function when x0 is going to be equal to 0.05, then it's kind of difficult for us to evaluate this without a calculator. So what you have to do is you have to evaluate this at the point 0.005, which is going to be square root of 1.005. So what we want is we would like to approximately evaluate the value of the square root of 1.005, and that's what we are going to discuss today. So the idea is going to be like this. So let's say I've got the graph of this function, which looks like this, which passes through these 2 points, essentially from the -1 and 0, and the 0 and 1. So still we've got this function f of x is equal to the square root of x plus 1. Well, if you substitute the -1, you're going to get the 0. If you substitute the 0, you're going to get the 1. And it's kind of very easy to evaluate this function at this point, right? At this point 0. At the 0, it's going to be simply equal to the 1. So now, let's say what I want is I would like to evaluate this at some point very close to the 0. So at the point x0 plus the h, which is in our case is 0.05. So what we have to do is we just need to know what is the height of this curve at this point. And it's difficult for us to do this manually. So what we want is we would like to approximate this. So the idea would be to sketch the tangent line at the point x0. So since we know how to evaluate the function at the point x0, we can find its tangent line as well, so the equation of the tangent line. So in our next step would be, so instead of saying, hey, so instead of evaluating f of x0 plus the h, I would like to evaluate the value of the tangent line here. Okay, so let's assume you've got the tangent line. So the tangent line of this curve at this point, let's say, is going to be some function L of x. And we are going to say that, hey, f of x is going to be approximately the same as the L of x near the x0. So you can see here that the heights of these 2 points are very close enough. And since the tangent lines are always given as a linear function, it's like a kx plus b, we can always evaluate the values of the tangent lines. So this is the idea. So the idea is, so we know how to evaluate the function at the point x0, and we would like to approximate this at the point x0 plus the h using the tangent line. So instead of evaluating the function itself, we are going to evaluate the tangent line. Okay, so what we need to do is we need to first of all derive the equation of the tangent line at this point x0. And if you remember, so any equation of the line is given as, so we are going to denote this as L of x. So it is going to be as a kx plus b, where the k is going to be the slope of this line and b is going to be the y-intercept. So the slope of the tangent line is nothing else as the derivative of this function at this point. So it's going to be the derivative of the function at the point x0. Okay, and if you and let's assume that you are given this point here, right? So we're given this point, which is actually x0 and f of x0. And we know what is this. So for example, in a case of our function, x0 is equal to the 0, and we've also calculated that f of x0 is equal to the 1. So we know how to do this. So we're going to denote this in general as the x0 and f of x0. So if you substitute x0 and f of x0 to the equation of the tangent line, it should work, right? Because you see, so this point, this tangent line is passing through this point as our curve as well. Okay, so we are going to substitute this point into the tangent line in order to find a b. So the b is going to be equal to f of x0. So I'm just going to substitute L of x, or y was the f of x0, minus kx0. Okay, if you substitute x0 and f of x0 to this function, it should work. The left hand side should be equal to the right hand side. Okay. Cool. So since we know what is the k, I'm just going to substitute the k to here in order to find the b. So the b is going to be equal to f of x0 minus f prime of x0 times the x0. So now we know what is the k and what is the b. So I would just substitute this to the equation of the tangent line. So the L of x, or we can denote this just the y, is equal to k, which is f prime of x0, times the zx, right? So instead of k, I've substituted the f prime of x0. So plus, instead of b, I have to substitute all of these terms, which is going to be f of x0 minus f prime of x0 times the x0. Okay, so you can see here that I've got two f prime of x0s. I can take them out from the brackets and I will obtain a simplified equation. It is going to be f of x0 plus f prime of x0 times the x minus x0. Well, that's going to be the equation of the tangent line. So here you see, so this is a linear function because on the left hand side you've got just the power of the x. So x is a variable and all of the other terms are the constants. So the f of x0 is going to be calculated. F prime of x0 is also going to be calculated. x0 is going to be given. Okay? So the only variable is here the x, and it's a linear function. So approximating the function using a linear function is called a linearization. And linearization of any function y is equal to the f of x at the point x0 is going to be found using this equation. So this is what we call as a linear approximation of the functions, or linearization. What we wanted to do is, I would like to show you a couple of examples of evaluating this function and using this function. So let's go back to our example. So where we needed to find the square root of 1005, right? Or 1005 or 105, it doesn't matter in this stage. So what I want is, I would like to first of all obtain the linearization of this function. So I need the derivative of this function, and also I need the derivative of this function at the point x0, which is 0. Right? So the derivative of this function is going to be equal to 1 divided to the 2 square root of x plus 1. So if you evaluate this at the point x0, which is 0, it is going to be equal to the 1 over 2 simply. So the linearization is going to be equal to f of x0. So what is the value of the function if x0, if x is equal to the 0? Right? It is equal to the 1. Plus f prime of x0 is equal to the 1 over 2 times the x minus x0 is equal to the 0. Well, it's going to be simply 1 over 2x plus 1. Okay? So now, if you evaluate the L of 0, so we have to evaluate L of 0.05, right? So at the point 0.05, our function is going to be 1.05, right? Which is going to be equal to, so 1 over 2 times the 0.05 plus 1, which is going to be 1.025. So this point can be a little bit confusing. So this point, right? So f of 0.05, so here's our function. If you substitute x with the 0.05, what you get is square root of 0.05 plus 1, which is square root of 1.05, right? So you can obtain 1.05 from the square root from your function if you substitute x to be equal to the 0.05. Okay, so this is going to be our approximation. And if you now go and take a calculator and calculate what is the square root of 1.05, you're going to get roughly 1.024 and 67 or something like this, which is going to be very close to this. Okay, so again, the idea is approximate function using a linear function, using a line, right? We show this, why this is true in the graph, when it is not possible to do this. So I would like to show you another example where the linearization might be useful. So we know this limit of the sine of x over x when x goes to 0, right? So we've discussed it so many times, and it's very difficult to evaluate this right immediately by just substituting x to be equal to 0, because if you do this, you're going to get 0 over 0. Well, you can prove that sine of x over x is equal to 1 with different methods. And one of the methods how we can do this is the linearization. What I want is, I would like to find the linearization of the sine of x at the point x0, which is equal to 0 simply. And then I'm just going to substitute the sine of x with its linearization. So what I want is, I would like to substitute the sine of x with its linear approximation near x0 at the point 0. Okay, so in order to do this, I'm going to use this equation. And in order to use this equation, we need a couple of values. So the first one is the derivative of this function. Our function, please note, is given as the sine of x. We're finding the linear approximation of the sine of x for now. So this is going to be equal to the cosine of x. And at the point x0, which is 0, is going to be equal to 1. So now we can evaluate the linearization of the sine of x. It's going to be, so what is the value of the sine at the point 0? What is the sine of 0? It's 0 plus the derivative of the sine, which is cosine, at the point 0, it's 1. 1 times the x minus, so the x0 is 0, it's going to be 0. So, well, it's going to be simply x, okay? So the linear approximation of the sine near the x is equal to 0, it's going to be simply x. So what we can do is we can say that the limit of x goes to 0 of the sine of x over x is roughly equal to the limit of x goes to 0 of x divided to the x, because sine is approximately equal to the x near the x is equal to 0. And that's going to be equal to 1. So this is one of the interesting ways to prove that the limit of the sine of x over x is going to be equal to 1. Well, this was the linear approximation of functions. So later on, we're going to learn about the quadratic approximation or the cubic approximation of the functions. And all of these approximations are going to be done using derivatives.